So the following is an introduction in adding trend lines and curve fitting in Excel. Suppose we have some XY data where the Y data is a sine function with some random noise that's added using the rand function. The rand function creates a random number between 0 and 1. The way I add a trend line to the data is I plot the data, so highlight it, insert, scatter plot with just data points. And I right click the data points and there's an add trend line feature. If I click add trend line, then it puts a trend line on here and gives me several options. There are options for linear, exponential, logarithmic, polynomial, power law, moving average. Here if we put a polynomial, we can choose the order of the polynomial. It'll go up to 6th order. Let's choose a 2nd order polynomial. And then there's a number of options available. We can set the intercept to be whatever we want. Suppose we know the intercept is supposed to go through 0, so we can set it to 0 or anything we like. We can show the curve fit of the line on the chart. We can also display the R² value, which is a measure of how good the fit is. Let's go ahead and increase the size a little bit. If we right click on the trend line, we can format the trend line label. Then on the trend line label, we can choose how we want to format the data series. So if we want, we can use a number and choose the number of decimal points. We can use a scientific notation, anything we like. If we double click on the trend line itself, we can change properties of the line width, the line style, line color, etc. like usual. So to include a trend line is pretty simple. We just plot the data, then right click on the data points, add trend line, and then select the options that we want on the right. The reason why we would want to include a trend line would be perhaps to simplify the data, so we have a simple representation of our data points. It can also be useful if we have a model that we want to fit to our data, and perhaps we want to use the trend line in order to evaluate y values for which there isn't a corresponding x value. The R² value provides a measure of the goodness of the fit, so let's go ahead and look at that a little bit more. Let's do another trend line. So highlight the data, insert a plot, scatter plot, right click, add trend line. Here let's go ahead and add a linear trend line, display the equation and the R² value on the plot. And increase the size a little bit. And maybe we'll right click this format trend line label, and then we'll go and make this scientific with maybe 6 data points. So if we have this, we can now evaluate our own data series with the model, which is our trend line. So we can enter the formula 8.414477 e to the minus 1 times x plus 3.5538 e to the minus 2. And this would be our modeled data. Now the R² value, there's a function for that. It's called RSQ. And we can evaluate that directly in the sheet if we have our data points and our fitted data, our modeled data. So we type equals RSQ, and then the y values, those are our known y's, and our known x's aren't the x data, that's the modeled data. So comma, the modeled data. They're calling it xy because you have 2 series. And in our case, our series are y and z, which are our model. And we hit enter, and we get RSQ is 9.98667, which is the same thing that we got on the trend line. There's another function called correl, which is the correlation coefficient, and we can use that similarly, equals correl of our data here, H3, H23. And if we square that, that's the same thing as RSQ. So the correlation function squared is the same as RSQ. This R squared value, R is the correlation coefficient, and that's defined as the covariance between Y and Z data divided by the sigma Y and the sigma Z. So it's like a normalized covariance. If we had a perfect agreement between our data and the curve fit, the correlation coefficient squared, R squared, would be 1. And if we had perfect anti-correlation, we'd have a value of -1. So you're kind of looking to see how close is this number to 1 to see how good your fit is. Let's look at another curve fit example. Here, this one's bacterial growth, and we have 2 bacteria, and given are the concentration of the cells and the corresponding time, and we want to fit that to a model. The number is the initial plus e to the t over tau, where t is time and tau is the intrinsic growth rate of the bacteria. I'm sorry, the intrinsic growth timescale of the bacteria. So we would highlight this data. Highlight the data, then we can go and insert a scatter plot. Right click on the data points, add trend line, and here we'll add an exponential trend line because that's the kind of data we have, an exponential function. And let's display the equation on the chart. So in this case, the value of N0 would be 10.149 according to the best fit, and we're comfortable with that because it's similar to the actual value that was measured at time 0. So the curve fit fits that quantity, and here we've got the value as well. E to the 0.0587, this value 0.0587 is the coefficient of x, which is the coefficient of t, which is 1 over tau. So we have 1 over tau, 1 over tau equals 0.0587. So if we want tau, then we just take 1 over that. So tau is going to be equals 1 over 0.0587, 17 minutes. And we can kind of see that that's makes some sense if we look at the data. Most of the action here happens in about, if we look at this spread, in around 17 minutes. If we want to look at the other bacteria, because the x-axes are the same for both, we can just move this over. Now we're plotting the other, and it automatically updates the trend line. And now the other bacteria's tau is 1 over 0.0359, so equals 1 over 0.0359. We get 27.86 minutes. So this is an example where 1 over tau isn't, the value that's given isn't the parameter we want, it's related to the parameter that we want, because our parameter is 1 over tau instead of this coefficient itself. Let's look at a slightly more complicated example. Here we have chemical kinetic data where we have time in minutes and concentration in mole per meter cubed, and we want to fit the data here to the following function in order to find the value for 2 parameters, C0 and K. In this case, there are no trend line options that have this form. So our only options are, well, so the thing that we would like to do is modify this equation so that we can use one of the trend line forms that are given. So if we do that, we can say 1 over c, let's move this 1 over c naught parameter to the right hand side. So we have 1 over c equals kt plus 1 over c0. Now if we call the value, the parameter 1 over c, if we group that and call that y, we can write y equals kt plus y0. Now we can see that our data is linear if we put it in this form. So we have a slope and an intercept. And our intercept is going to be y0 equals 1 over c0. So we can say c0 will be equal to 1 over y0. and our k will be the slope. So let's go ahead and plot it in this form. So we're going to write 1 over c, and we go equals 1 over c. And if we plot that versus time, we can insert chart, scatter plot, right click, add trend line, add a linear trend line, display the equation on the chart, and then we'll right click the equation, format trend line label. We'll use scientific notation with maybe 4 significant figures. And then we have our slope, which is 9.6 e to the minus 6. That will be k. So we can write k as 9.605 e to the minus 6. And c0, well, y0 is 1.0472 e to the minus 3, because that's what we were computing as our intercept. So if we want c0, we just go equals 1 divided by 1.0472 to the minus 3. We get 954. And that's consistent with the concentration at time 0. So this is an example where sometimes you have to look at the model you're fitting and see if there's ways that you can group or change the equation so that it will fit one of the forms that we're interested in. Let's look at another example where that's not possible. Here is the Antoine equation, which relates vapor pressures of a chemical species to the temperature. The Antoine equation has 3 adjustable parameters, A, B, and C, and we have data. In this case, we have data for, let's start over here. In this case, we have data for the temperature, and we'll get rid of this too. We have data for the temperature and the pressure. So that was the raw data that was given to us. And we want to find the values for A, B, and C. So what we're going to do is say, let's compare the left-hand side of this equation, which we know, those are the model data, with the right-hand side of this equation, which is going to be our modeled values. And then we want to adjust these parameters so that we get the best fit between the model and the data. So this left-hand side column is equals log 10 of our raw data, that's the pressure. And the right-hand side is just the model, so we can type A minus B divided by quantity temperature plus C. And we've named these cells A, B, and C underscore so that we can use just the names. And we highlight these and double click, and then we've plotted, on the plot we've compared the temperature to the real data and also the modeled data. So the symbols here are the raw data, and the line is the predicted value given A, B, and C. And we can see that our choices for A, B, and C aren't very good because the red line doesn't go through the blue data. So the way that we can get a better agreement is to compute the error for every data point. So we're going to compute the error between our model and the data for every point. And we don't want the error because the error could be plus or minus. Instead, we're going to make the square error so that it's always positive. So we can do equals our model minus the raw data squared. And we'll do that for every data point. So fill down by double clicking. And then we want to compute, so that's a measure of the error at every single point. But let's get the overall global error. So if we sum all that, so we have the square error and the sum of the square error, if we add all of those, sum of these points, sum that, then that's our sum of the square error. So we want to make this as small as possible. if the red line went through the blue line, then we'd have a small error everywhere, and the total error would be small. So what we're going to do is use the Excel solver, and we're going to tell the solver to make this cell as small as possible by varying our three unknowns. So let's go up to the solver, data, solver, and we're going to set our objective, which is the sum of the square error, make it minimum by changing our variable cells, A, B, and C. Whoops. Our variable cells here, A, B, and C. In this case, we don't have any constraints, and we hit solve, and it found a solution, and we can see that the sum of the square error is much smaller now, and the coefficients that it found for A, B, and C allow our model to go really nicely through the data points. So this is a really nice technique. So basically all we did is took our model and we plotted the real data, which was the left-hand side, versus the model on the right-hand side. Then we compute the square error at every point. We find the sum of the square error, because that's sort of the global error. And then we tell the solver, make that global error as small as you can by varying all three of our parameters. We should note that you can also solve systems of nonlinear equations this way. If we had suppose we had variables x, y, and z, and we had values for those, guesses 5, 6, and 7, and then we had three functions of those variables, f1, f2, and f3, and of course we can't have that. Let's left and no color and not bold. Okay, and we put some function in there equals some stuff. Okay, so let's say the value was 0.2, 2, and 3, and we want these functions to all be 0. So in Excel, we've seen how we can tell the solver, make this cell 0 by varying these, subject to the constraints that these are also 0. But another way to do that is to recognize that if the function is supposed to be 0, then 0.2 is the error, and 2 is the error, and 3 is the error. So we can find the square error equals the value squared. These would be the square errors. And we could find the sum of the square error equals the sum of these. And then we could tell the solver something like, this won't work, but to illustrate it, if we go to the data, we could go to the solver and say, make the sum of the square error, make it as small as it can be by changing our variable cells, x, y, and z, and we wouldn't need any constraints. And if we hit solve, then it will adjust these so that the square error is as small as it can be, and that'll make the functions effectively 0. So we can use this same technique for finding coefficients, where we're just trying to minimize the error between our model and our equation by varying the coefficient, by varying the parameters, or we can solve systems of equations that way.